5.2, mean value theorem. Now, this one is specifically for derivatives. There will be a mean value theorem for integrals later on, but don't need to worry about that right now. So it connects the average rate of change of a function over an interval with the instantaneous rate of change of the function at a point within the interval so the actual mean value theorem, and we'll often abbreviate it MVT, and this is for derivatives because like I said there will be another one later. Says if y equals f of x is continuous at every point of the closed interval a to b and differentiable at every point of its interior so basically the open interval a to b, so just not including the endpoints, then there is at least one point C in the interval a to b at which f prime of c is equal to f of b minus f of a all over b minus a. And this is an existence theorem. Just because something would it be existing within that. All right, next we're going to look at increasing and decreasing functions. So definition, let f be a function defined on an interval. And I'm going to call that interval capital I, and let x1 and x2 be any 2 points in I, so in that interval. Then f increases on I if x1 is less than x2, which would then imply that f of x1 is less than f of x2. So kind of just makes sense. And 2, f decreases on I, excuse me, if x1 is less than x2 implies f of x1 is greater than f of x2. So basically for the same, like for x and y, or for the two x values, as x is getting bigger, what's happening to the function as a whole is what that means. So yes, those inequalities are facing the correct direction. So basically in the first one, it's saying that the first x value, the y value of it is less than the y value of the second one, because as x gets bigger, it would be going up. And then the other one, as x is getting bigger, y is going to be going down. To like think about it visually for it to make sense. All right, the mean value theorem allows us to identify exactly where graphs rise and fall, functions with positive derivatives are increasing functions, functions with negative derivatives are decreasing functions. All right, we have a corollary for increasing and decreasing functions. Let f be continuous on the closed interval a to b and differentiable on the open interval a to b. 1, if f prime is greater than 0 at each point of a to b, then f increases on the closed interval a to b. And 2, if f prime is less than 0 at each point of a to b, then f decreases on a to b. So I'm actually going to prove this one for you, just for you to see it. So the proof, let x1 and x2 be any 2 points in the closed interval a to b, with x1 less than x2, the mean value theorem applied to f on the closed interval x1 to x2 gives f of x2 minus f of x1 is equal to f prime of c times x2 minus x1 for some c between x1 and x2 the sign of the right hand side of the equation is the same as the sign of f prime of c because x2 minus x1 is positive. Okay, and we know that because x2 is greater than x1. Therefore, so when you see the three little dots in the triangle, in case you've never seen it before, that means therefore, part 1, f of x1 is less than f of x2 if f prime is greater than 0 on the open interval a to b, which implies that f is increasing. And part B, f of x1 is greater than f of x2 if f prime is less than 0 on the interval a to b, then f is decreasing. All right, we're going to have a couple corollaries here. The first one, functions with f prime equal to 0 are constants. So if f prime of x is equal to 0 at each point of an interval I, then there is a constant c for which f of x is equal to c for all x in I. Oh, yep, sorry. Is that enough? Okay. All right, the next corollary is for functions with the same derivative differ by a constant. if f prime of x is equal to g prime of x at each point of an interval I, then there is a constant c such that f of x is equal to g of x plus c for all x in I. And the proof for that is going to be on page 204 if you wanted to look at it, if you were just so curious about it. Can I scroll down past the purple? Okay. I just have one derivative, one definition left. I think. Definition. A function f of x, and it's a capital F, it's not that big of a deal, but is an antiderivative of a function f of x, which is little f of x, that's why I said that one's capital, the other one's lower, if f, capital F prime of x is equal to little f of x for all x in the domain of f. This process is called anti-differentiation. So this is doing the opposite of taking the derivative. So I'll give you an example of what that looks like. I'm going to do an easy one to start with. So if you were told that the derivative was equal to 2x, we would want to work the opposite way. Okay, so normally we take the power, we throw it out front, and we subtract 1 from the top. But what we do in this case is we want to work our way backwards. Now, there is a possibility, okay, what this corollary up here said about a function with the same derivative differ by a constant is that when we take the derivative and we have, like, say 3x squared plus 2, when we take that derivative, right, that plus 2 part just goes away, okay, because the derivative of a constant is 0. So when we take the antiderivative of the function, we don't know whether or not there was a constant, and we don't know what it was. And so that's where the plus c part comes into play with the antiderivatives. So if I tell you that the derivative is f prime of x, I want you to tell me what the original function was. Okay, that's what this is doing. That's what the antiderivative is. And there will be a lot of rules because there's things that you're probably thinking like, well, we took some derivatives of some pretty crazy things. Like, how do you get back to that, like, to figure that out? There will be a lot of rules for things that are, like, crazy, quote unquote. But the antiderivative of this Basically, we take whatever we threw out front and put it back up top. Okay? And so this would become x squared. But, like I said, we don't know if there was a constant or not. So on every problem, you need to write plus c. Okay, the plus c part is critical. If it's not there, your answer is wrong. Now, that constant could end up being 0, but because we don't know, that's why it has to be there. Trying to think of another example just so you can see it to be familiar with it. If they started you with the derivative, they said f prime of x is equal to 1/2. Okay, we want to figure out what the original function f of x was. So if there's no variable here, what does that mean that the power was of this problem before? X to the first, okay? So this is going to end up being just 1/2 x, okay? Because right now we have x to the 0, so we essentially added 1, and then we're going to add that plus c. So when you take the derivative back, you should always get back to what you started with. So if I took the derivative of what's in red of 1/2 x plus c, c is going away because it's a constant. Derivative of that is 1/2, the 1/2 x part, okay? The derivative of x squared is 2x. Derivative of the constant is 0, and so we get back to the original. Now, there's another scenario that we could have. Also, I should probably clarify before I do that. When I said we put this number up top, obviously that's where that came from, but we're technically just adding 1 to whatever the exponent was. In this case, it was easier just to say put it back up top, but that's not exactly what's happening in every situation. Let's look at one other situation, then we'll probably stop for today and we'll just do examples tomorrow. So hopefully, what's up? You made it back fast.
So I was able to get seen early.
Oh, that's good. You can just put it on my desk. Thanks. So f prime of x is, let's do x to the 4th. And so I'm trying to find my original, okay? So I'm trying to go back and find f of x. So what do I know the power of my original function had to have been for it to now be x to the 4th? I subtract 1 when I take the derivative, so when I do the antiderivative, it's going to be x to the 5th. Okay, you add 1. Antiderivative, we add 1. All right, so this is x to the 5th. I know I'm going to have the plus c. Now, this is why I say it's really critical that we check, once we've done our antiderivative, that when we take the derivative back, we get to what we started with, okay, what's in blue. So, Josh, what did you say that you thought the antiderivative was? You said something x to the 5th, I thought.
No.
You didn't? Okay. I was hearing things. Okay, well, that's good. I'm glad you didn't. So, what we need to do is we're trying to get from here to here. But if I take the derivative of this as it sits, ignore that's in blue, what would the derivative of this be here?
5x to the 4th.
5x to the 4th. But what do you notice between that and this? There's nothing in front. So what might I need to do? Sort of. What'd you say, Christian? Say it louder.
Christian says to put a 1/5 in front.
Put a 1/5 in front. If I do that and I take the derivative, now what happens?
Now it equals x to the fourth.
It equals x to the fourth. Okay, so antiderivatives often end up with fractions out front. Okay, because of things needing to cancel. Now, that's why I thought, the reason I said, what did you say? Because I thought you said 5x to the fifth when you originally said it. And that's why I was like, that's not going to give us the right thing. Okay, so Nathan, what we were saying before is we have to have this plus c because we don't know if there was a constant in our original function. So we're doing the opposite of taking the derivative now. We're working backwards. So I was just doing a couple examples within the notes so that everybody knew what was happening before we get into the craziness of it all. So I'm going to say any questions, but be hesitant to ask. No, I'm just kidding. We haven't done a lot yet, so you probably do have questions. Once we actually do the examples that go with it, it'll be easier than you think it is, at least in this section. I'm not gonna promise that antiderivatives will always be easy because there's a whole set of antiderivative rules that you're gonna eventually have to know when we get to integrals, because basically taking the integral is taking the antiderivative of the function. So fun. All right, well, we're going to stop there. We'll do examples tomorrow. Hopefully, we'll have everyone to go through it because mean value theorem's not hard. It's basically just plugging stuff into that formula, which is nice comparatively to what we had been doing. And we can even do some word problems using the mean value theorem that are actually really easy. So overall, the math for this section shouldn't be that big of a deal. Antiderivatives, I only did ones that had like one term, but they could have 4 or 5 terms. We could do the antiderivative of trig functions, antiderivatives of logs, all those lovely things, but we won't be doing them of like quotient rules and stuff yet because you don't know how to do that yet. And this section doesn't teach you that.